Thanks for getting here on time. So then our next speaker is going to be Ásgeir Eiriksson from Apple, and he's going to be talking about Ken's contributions in industry.
Yes, so a quick introduction. I've been at Apple for 8 years. Before that, I was a hardware designer, designing 9 chips. And before that, I did formal verification for 4 years. So I come, so mine is a different perspective from what we've been listening to this morning. My questions are always about how to fit this into the design process. Can we recreate the great results we see in papers out in the wild? Like, can a regular user be productive in these tools? And I was fortunate enough to intersect with Ken's career twice at critical time on the design side. First, when he moved out to California back in 1994, started working for Cadence Berkeley Labs. And then the second time when I had joined Apple, we again got ourselves into all kinds of trouble doing cache coherence protocols. And this time, Ivy was instrumental in saving the day again. In addition, we've gotten a lot of mileage out of Ivy in studying memory consistency on the SoCs. So so we started looking at Ivy for memory ordering verification, but then our model checking tool ran into issues with the cache coherence protocol, and at that time we were up to speed on Ivy, and so we could use Ivy to tackle those issues. So the first iteration of this is Silicon Graphics. It did cache coherent directory-based systems with up to 4,000 processors, because a lot of people mentioned, at least 2 people mentioned Flash this morning that came out of Stanford. Dash was the one in before Flash, and those people then went to do the STI commercial version of that. And one difference I always see when I listen to presentations on cache coherence, on the industry side, there's like one additional critical component, and that's when the data comes into the coherent domain and when it leaves the coherent domain. Like the STI machine had cache coherent I/O, and that was built into hardware. So that was an integral part of the cache coherence protocol. So the block diagram showing the fabric and the processors and the memory. In addition, there should be an I/O processor there. So, and this is how things happen in industry. On the silicon side, something called shared memory bus architectures with up to 8 processors. They're about to hit the limit, the clock limit, and people had invented directory-based coherence protocols, so they decided to build that machine, even though they knew that the simulation was running out of steam in verifying the shared memory bus architectures, and they knew they would get into trouble when they tried to verify the directory-based protocols. So early 1994, I'd been working on an SMB model of the new protocol for maybe 6 months, and then management came out with a directive just about the time you were moving to the West Coast. 6 months, you find the bug, or you scrap model checking when you go back to simulation. And my recollection is we found the first one maybe with a month to spare, and then went on to finding various other ones. And interestingly, relates to my previous comment, most of them were interaction of I/O and CPU, because those are different camps. CPU for show, I/O for do. There's like a divide in between. That's where the bugs show up. So yes, so like several bugs, and then because this was perfectly aligned in time, the lead designer on this chip, or one of the chips, he left the company. So I moved over to the design side, and that's when Cadence Berkeley Labs SMV showed up. And so I was in the position as the FE guy and the designer to test out all the great features of the Cadence version of SMV. Before I was done, I had used the inductive features to prove that the protocol was correct for all possible configurations. And for that, SMV relies on symmetry to reduce the number of lemmas. My recollection is about 8. And that's how you prove the induction step, when you prove the correctness. And the largest model checking problem had 3 of these nodes, 3 CPUs, or like a total of 3 CPUs plus the I/O part of it. And then because I was the designer also, I was able to take one of the modules in the coherence protocol, the high-level one, and refine that down to the actual implementation. Thought to be huge at the time, like a 1,000,000 gate chip. Now there are, I think, 3 additional zeros been applied to it. And the tough observation when it comes to refinement, and can observe this way at the front. If you're the designer, you know exactly where the state in the high-level model goes in the RTL. And that puts the designer then in a unique position to do the refinement of the design. But very few designers have interest in FE to that extent. So there's a catch-22. And since then, what I see in Apple is there are many specialists in formal verification, and there's a big shortage of people that are studying hardware at this point. So a considerable number of the FE people at Apple, those are people that really want to be doing FE of software, but they're being transformed into doing FE of hardware. And when I look back, the model checkers that are popular today, they're missing many of the crucial features in SMB, Cadence SMB. And it comes about because the companies, they had to sell number of seats. So they emphasize the GUI, they emphasize libraries that come with it. In effect, they have come to a conclusion that it's not worthwhile dollar-wise to attack the tougher problems where the full potential of FE would be released. Then Apple 2017, and so you have what has been analyzed by Ivy in these products shown on the right side. What happens in this environment is that the cache coherence protocols, they have very many power optimizations. And that's why model checkers have issues with it. And as I mentioned, the SOCs, like the iPad, is very comparable to the picture I had on page 2 with the 4 like my size racks of machines. You have the same amount of hardware in an iPad, and there are like many opportunities to screw up the memory consistency in the SoC, and you can guess how we came to that conclusion. And that's why it was absolutely crucial to find some tool that was efficient and at formally verifying memory ordering. So this is how we came at the conclusion that we needed Ivy. We tried to approach it the same way as with SMV, but instead of needing 3 processors to get into all states, this protocol needs 5. But model checking is still only tractable for 3 or 4. So, and you're gonna sell 100 million units. That's Apple's goal for every SoC. So there had to be something that we needed to do about this, look for other ways to do the verification. And so we were aware of the FM CAD paper, and that from 2016, and that one was really the inspiration for using Ivy for the ordering model, because the EVS structure in that paper is really just a one-to-one match for the information you need to keep track of in an ordering model. Issue time of requests, arrival time at various intermediate hops, and so this was how we started using Ivy. We got into trouble with the model checker. We were aware of Ken's paper that was really eye-opening, I think, for me, because it was really surprising that the EVS is still within the desirable fragment of the logic of that structure. So the first thing I did was, is this usable in the wild? So this is 2017, 2018. So I took the SGI protocol that I knew and looked at the papers that described it, and I developed in about a week an Ivy model for that protocol. Little did I know, I didn't even know then that some of the issues that we would uncover, like with Casper protocols, there are always unknown unknowns before you FV. And so, in effect, oh, okay, this took a week. This looks like it's doable without too many headaches. And so this went on to develop the Ivy model, and initially for the first 4 or 5 years, it only had safety properties. And when I look back at the models, the ordering model is about 10,000 lines of Ivy code. The coherence model is also about 10,000 lines of code. It's really premised on 2 things. It's the main refinement strategy pointed out by Ken many moons ago, maybe 1995, is that instead of like design state, pipeline state, you have 128 bits move from pipeline states P0 to P1 to P2. For model checking purposes and refinement purposes, it's much more efficient to keep around 1 copy of the state, and then you write the refinement map that tells you where it's at currently. And the other key thing that all these models are based on is the EVS structure from the FMCAD paper, which was maybe the first Ivy paper. I'm not sure. So 2 years ago, we at Apple, we came to a conclusion that we really wanted to figure out how to do liveness. I know Odette is sitting here, but with no, when we used the initial, what we call the machine level liveness proofs, we always felt like we were sweating blood when we got those proofs to go through, even for very small proofs. And it was just a daunting task. We sized up the ordering model. We're going to need 200 liveness proofs. That's the size of the ordering model. And there's no way that was going to scale. So Ken came and contracted at Apple 2 years ago using a subset of the ordering model that is part of the Ivy repository. And that led to his paper in last year's CAV. And this, for us, really improves the productivity of the liveness proofs by at least 10x, and allows us to do end-to-end proofs in the ordering model and the CAS coherence model using the same tactics. And what we see is that it really improves the code. And so in the process of proving the liveness proofs, drastically improves our confidence in all the safety properties that we've proven in the models. And yes, it cannot be overemphasized. Ivy allows us to do this with productivity so that Apple September is every year, so this is repeated every year, and Ivy allows us to keep up with that design cycle. There are gradual changes in all the protocols, and so every time we have to re-verify the whole thing, and because of the decidable logic and the counterexamples that get produced, to a large extent, we can just put in the changes and then test out what needs to be changed. There's a drastic difference to what the theorem proving people would need to do in the same situation. Well, that's it. Yes.
You made an interesting observation that hardware engineers at Apple
Yes.
are not vested in FV.
The
people who are very passionate about FV are FV enthusiasts themselves. Yes. So I was wondering, why don't the FV enthusiasts just take over the hardware implementation?
So what I meant to say was that there are not many hardware engineers that are interested in formal verification to the extent that they achieve the expertise required to do some of these things, yes, to do refinement. Then you look at just the supply of people that do formal verification. Vast majority of, almost all of them, are on the software side. They want to do software.
They're not interested in doing hardware design.
Well, they're made to become interested. They get job offers to do formal verification on the hardware side, but all the buzz is on the software side, like blockchain, FE, all those things. So we see this when the candidates that come, it's the very few hardware people.
I've had many conversations over the years with people at KenFest, and the argument there is it's a different